Hello, this is Mr. White, and this video is on evaluating limits analytically. And by now you should have at least a sense of the idea of what limits are, presumably through our lessons at the end of pre-calc. And if I had a function f of x that looked like this, and let's say this was 5, and this y value was 3, we should have an idea that even though f of 5 equals undefined, because we've got a removable discontinuity there, we should have a sense that what limits do is they ask the question what happens as x approaches 5. We don't really care what happens when we get to 5, we just care about the approach. So the limit of f of x as x approaches 5 equals 3. We may never get to 3 as a y value, but we'll at least approach it. Okay, so now we're going to start focusing on how to deal with limits analytically. And here are the 4 exercises I'll do in this video. So this first example is one that's just supposed to demonstrate or establish some properties of limits from the beginning. It's not the most exciting example, but it needs to be done. It needs to be understood. It's fairly intuitive to many people, and we have some theorems here in our book that just basically say that when you have the sense of, can I do that with limits? Does that really make sense? Am I allowed to do that? These theorems are intended to say, yeah, you can do that. It makes sense, it's intuitive, and yes, you are allowed to do it. So rather than belabor these charts that I just put in front of you of theorems, I'm just going to say, let's just demonstrate what these theorems tell you you can do. And hopefully you can make that connection when you look at those theorems in your book. All right, so we are given some information. We are told that these are some true statements. And I really want to encourage you, as I did in pre-calc and as I will continue to do in AP Calc, I want to encourage you to think of these graphically. Because really calculus and to a larger degree, a lot of math is all about images and shapes and graphs. And if you can't make that connection just easily and effortlessly, then a lot of your job becomes a lot harder. So let's say that, let me do some color coding here. Let's say that f of x, whose limit we have here, looks something like this. And let's say that this is c. This is x value c, which you see right here. And according to this statement, we are told that the limit of f of x as x approaches c is 5. So the y value must be 5. Now I drew it filled in here initially. I'll remind you, I could leave it filled in, or I could come in here and make a removable discontinuity here. It makes no difference to this limit statement right here. All right, and similarly, we have a function g of x whose limit at the same x value c, as x approaches c, is 8. So let's say here's 8, and I'll go ahead and just leave this one filled in, and let's say g of x looks like this. Okay, so part A here asks, what is the limit as x approaches c of g of x over 2? And I'll point out that all these limit questions involve x approaching c. Doesn't have to be the case. One could try to ask questions where x approaches something other than c, but we're going to keep it simple here. So you probably have a hunch as to what this value is, and let's just demonstrate that your hunch is probably correct. This is a vertical shrink of g of x. When you take g of x and you divide it by 2, you vertically shrink it. And that means every single y value on g of x, I'm looking at the green graph here, and I'm trying to draw something where all the y values are roughly half of what they started out. Or to even better demonstrate that vertical shrink, let me delete that and grab this copy here and vertically shrink it on the screen here. Okay, so there's our vertical shrink. All right, and so this is what g of x vertically shrunk by 1/2. If I've been saying vertically shrunk by 2, I should be saying vertically shrunk by 1/2. And that point, which used to have a y value of 8, now has a y value of 4, half of 8. And that is our answer. Or to just really make sure I made that as clear as possible, I'm taking this 8 here, and just like I divided the function by 2, I'll divide that limit by 2, and that's where I got my 4 from. So the limit as x approaches c of g of x over 2 equals 4. All right, I hope that one was clear. Let me move this down a little bit. And assuming that was clear, just to reduce some clutter, let me get rid of this, and let's try to do parts B and C a little bit faster. I hope you get the hang of what I'm doing here. The limit as x approaches c of f of x plus g of x. We're looking at part B here. And your intuition might ask, I wonder if I can just take the limit of f of x, which equaled 5, and add that to the limit of g of x, which equaled 8. Well, that would actually make sense, because when we picture adding two functions, f of x plus g of x, that means I add every single y value on both of these graphs to get the resulting sum. And I don't really need to focus about every single y value. I'll just look at what's going on in this region. If I took this point here, and even though there's not a point here, I can imagine adding those two and getting up here to 13, and that the points around them would maybe look something, well, see, the green graph is rising, the red graph is decreasing, so maybe you'd get something that looks kind of like that. I don't need to obsess over it a whole lot. I'll just go ahead and tell you that this intuition is true. We don't have to worry about what the entire resultant graph looks like. We're only concerned about approaching C. And we can be assured that, yes, the limit is 13. Okay, again, I encourage you in your book to check out these properties and see if you can make that connection to what we're doing here. The one we just demonstrated was this one. And even though the syntax may be a little bit intimidating, we're just demonstrating exactly what these properties say we can do. So finally, the last one, it's kind of hard to get our heads around what that resultant graph is going to look like graphically. Again, as much as I just said, I would encourage you to try to think graphically what that looks like. Sometimes that becomes a bit of an overwhelming job, and it's really hard to do. So here we're just going to rely on a comfort level with these limit properties. The limit of f of x as x approaches c is told to us is 5. And you may be wondering, I've got this 4 in front now. Can I just multiply that 4 times the 5? And yes, you can. And the limit of g of x was 8 here. And so since I've got g of x here, I'll put an 8 here. And since that 8 is being raised to the 1/3, or that g of x is being raised to the 1/3, do I just raise the 8 to the 1/3? Yes, I do. Again, look at the properties from our book, and you'll see that is, we are told that, yes, you may do that. So you just do a little bit of arithmetic here. 4 times 5 is 20. 8 to the 1/3, cube root of 8 is 2. 18 is our limit. Okay, these are not the most exciting problems, but it's important to really get these properties down. All right, let's go on to the next one. All right, this next one illustrates a property that I'm not sure how intuitive this is or isn't going to be to students. So let me introduce it right here quickly, and then we'll demonstrate it. This property discusses functions that agree at all but one point. So we're talking about two functions, f of x and g of x, which essentially equal each other for all values of x other than at x equals c. And the idea that you should envision here, what we should envision is, let's say we've got an f of x that looks like this. And let's say we've got a g of x that looks like this. It's the same graph everywhere except at some point c. And what that usually is concerning is a removable discontinuity at c. That's usually the case. And typically you're asked to find the limit of the g of x as x approaches c. And if you just try to plug in c, you're going to hit a removable discontinuity. You're not going to find anything there because there's a hole there. And so the idea is that if you can instead look at this f of x, where the hole has been plugged in, if you can instead take your attention away from g of x and look at f of x, where here's c, then all you have to do is look at the y value when you plug c in and say, oh, that's going to be my limit. I hope that made a little bit of sense. If it didn't, go ahead and stay tuned here and let's see if the following example can kind of clear that up. All right, so here's a function that I don't expect you to have any idea what that looks like. I'm going to go ahead and cheat a little bit and just show you what it looks like on a calculator. All right, so here here I show the window settings I have on my calculator, and you can see what the function looks like. And the thing I want you to look at very closely, I hope your screen resolution is detailed enough, is good enough where you can see that there's a hole there. There's a hole there that just happens to be at 6, at x equals 6. And we're supposed to find the limit as x approaches 6. Now, if this has not already been made clear to you, our first resort should be something called direct substitution. Direct substitution just says that everywhere where you see an x, put a 6. So there's all my x's, put a 6. 6 squared minus 7 times 6 plus 6. And I'll go ahead and tell you that that equals 0 in this case. And then on the bottom, I should have 36 minus 6 squared. That also equals 0. And this is what's called indeterminate form. That's called indeterminate form. That means you're not done. You're not allowed to just put, oh, undefined, I'm done. No, you're not. Indeterminate means we cannot determine. We've hit a dead end. We cannot determine what the limit is based on this result of 0 over 0. So we need to try something new. So let's do this instead. Instead of doing direct substitution and just plugging in 6, let's do a little bit of algebra. Let's factor that numerator. X squared minus 7x plus 6, let's factor that. That factors into x minus 1 and x minus 6, right? Let's factor the bottom as well. 36 minus x squared. That's our difference of squares. 6 squared minus x squared would factor into 6 plus x, 6 minus x, let's say. And let's not be lazy. Let's still remind ourselves this is a limit. This is where a lot of students just get lazy and stop writing limit. No, write the limit. And at first glance, you may feel like, okay, I don't see anything that we can do here. But I want you to look at it a little more deeply. Do you see something that divides out or cancels out? Look a little more closely and consider, just let me put off to the side. What if I had 5 minus 3 over 3 minus 5? When you have something in that pattern, a minus b over b minus a, what does that equal? That equals 2 over negative 2, or negative 1, right? So do you notice that that's essentially what's going on here? X minus 6 over 6 minus x. I want you to be able to recognize that. It doesn't come up all the time, but when it does, I want you to recognize that and go, oh, that's just negative 1. Or if you prefer to think of it this way, you could think, that's x minus 6. And if on the bottom I want to imagine factoring out a negative 1, that would leave me with a negative 6 here, because negative 1 times negative 6 gives me this 6. And that would leave me with an x here, because negative 1 times x gives me this minus x. Pause if you need to and make sense out of that. Again, I really need you to be able to spot that, because it will come up. Regardless, I need you to know that that x minus 6 over 6 minus x, that just becomes negative 1. So let's keep the rest of that. X minus 1 over 6 plus x. Now, here's the point where I need to pause and draw your attention to something. We've actually changed the graph a little bit in a very, very subtle way. We've actually changed the graph. But we changed it in a way that this theorem said is allowable. It says it's okay if I've changed the graph in a way that I've just changed it at one point, that one point C. So let's see how that theorem helps us out here. I may now plug in. I may now do some direct substitution. So now I can take this x approaching 6. I can just plug 6 in for x. I will find that it is not undefined anymore. So on the top, instead of x minus 1, I'll put 6 minus 1 over 6 plus 6 times negative 1. Notice I didn't write limit this time, because direct substitution I already knew due to experience that this would work. This is the y value that the graph is approaching. And if I turn my attention to the graph, again, the change that I really want to emphasize here is that by canceling out these terms, these were the terms that were causing the problem. These are the terms that when I plugged in 6 gave me 0 over 0. But by canceling or dividing them out, what that essentially did is it plugged in this hole on the graph. I now have a continuous graph. And if I can just ask what is the corresponding y value, which I'm about to find out, then that will be my limit. So let's do the calculation. 6 minus 1 is 5 times negative 1 will give me negative 5. And then on the bottom, 6 plus 6 gives me 12. I've just determined that the limit there is negative 5/12. Again, to recap, direct substitution originally didn't work, But then when I got rid of these terms that were causing the indeterminate form, the 0 over 0, it plugged in the hole. That theorem said that's okay, you can plug in the hole and evaluate the limit and you'll still get the right answer. So whether that hole is plugged in or whether it's not plugged in, the limit is negative 5/12. Okay, I hope that made sense. Let's move on. Okay, here's one that looks really ugly at first. And when we think about what we did in the last exercise of factoring, we look at that and go, I don't really see how that's going to factor. Okay, once again, I want to emphasize that our first resort with limits is to try direct substitution. Let's try just plugging in 5. Honestly, in a calc class, rarely is that going to work, but once in a while it will. We have to try it. It's our first resort, and if it works, we're lucky. But I say, okay, square root of 5 plus 11, that's square root of 16, that's 4, minus 4 over 5 minus 5. Once again, we've got indeterminate form. Okay, direct substitution didn't work. Let me go ahead and once again show you the graph. I don't expect you to be able to look at this one and have much success figuring out what that's going to look like without a little bit of technology assistance. It almost looks like a horizontal line given the window settings that I have here. We know it's not truly a horizontal line, but it certainly must have leveled out to quite a bit, given, at least in the view of these window settings. And once again, if you look really closely, you'll see there's a hole there. There's a removable discontinuity, and once again, it happens to be right at the value that we were interested in. We were interested in the limit as x approaches 5, and that just happens to be where I have my removable discontinuity. That's why direct substitution didn't work. We got 0 over 0, and that's where the hole is. Okay, so we need another algebraic trick. There's one here that's not terribly intuitive, and it's called using a rationalizing technique. You may have seen something sort of similar in Algebra 2, although a little bit different. Let me show you how it works. You may remember from Algebra 2 or elsewhere something called a conjugate. The conjugate is when you have something like, in this case, this radical minus 4. The conjugate of that radical minus 4 would be the same radical, root x plus 11 in this case, but plus 4. And I'll ask you to jog your memory as to what did that do for us. Well, if I'm going to multiply that numerator by this conjugate, I'm not allowed to change the function in any way other than possibly plugging in a hole, so I have to put that on the bottom as well. And at first glance, you may think, wow, that looks really messy and ugly. But let's see what magic it works. And let's go ahead and just focus on the numerator for a moment. Let's focus on foiling that out. And we should see our difference of squares pattern. That was the value of conjugates. Remember, you essentially on the top have like an a minus b times an a plus b. That's going to give us a squared minus b squared, right? I hope you know what I'm referring to. When I FOIL that out, if I just FOIL that out the long way, root x plus 11 times root x plus 11, that's going to just get rid of the radical and give me x plus 11. And here's the canceling out. Root x plus 11 times positive 4, but I'm not even going to bother writing that because it's followed up by a root x plus 11 times negative 4. That's what always happens with difference of squares. The outer and the inner products cancel out, and all I'm left with is then saying, okay, minus 4 times positive 4, that's going to give me minus 16. Let's do that on the top. I'm not doing direct substitution, so I do still need to put lim here. That's what I have on the top, and you may be wondering, okay, when I turn my attention to the bottom, to the denominator, should I FOIL that out too? And the answer is no. Let's just be patient. And that's kind of an instinct that you're going to need to develop in calc, is to when to FOIL and when not to FOIL. And I can't tell you any easy way to develop it. I will say just that in general, denominators I tend to leave factored, and many, many times in calculus, I find that does us favors. Let's see why it does us a favor here to leave it factored. Look at how the numerator simplifies. The numerator simplifies x plus 11 minus 16. That's just x minus 5. And in the denominator, I've got that factored. I'll just leave it factored. And now you're probably seeing why this was a good idea. Just for emphasis, I'm going to put a 1 there. Yeah, I'm not saying you have to, but I'm going to put a 1 there. The reason I like to do that is because now when I cross out or cancel out or divide out my x minus 5s, I see that the numerator has a 1 remaining. Let me once again draw your attention to the graph, which I didn't expect you to have to know in your head what that looks like, but using our calculator, that's what the graph looked like. And again, I want to really emphasize that the act of crossing out these x minus 5s, what that does is it changes the graph. It plugs in the hole, and that theorem that I alluded to earlier says that's okay, you can do that. So I can be sure that this remaining function still looks exactly the same, except it's got the hole plugged in. And that's going to allow us to do direct substitution. So let's go ahead and do some direct substitution. I'm going to take that x approaching 5, but I'm just going to plug in 5 where I have an x right there. And since I'm doing direct substitution, I don't have to write lim anymore. I'm just going to write 1 over square root of 5 plus 11, and then outside the radical plus 4. And that's going to give me 1 over square root of 16, which is 4 plus 4. My final answer is 1/8. What I've just determined is that the value, the y value that's being approached here, is 1/8. There's our limit. All right, I hope this is making sense. Again, in the book, they call that a rationalizing technique. It's similar. Hopefully you feel like that's similar to something you've done in Algebra 2. All right, let's go on to our last example or exercise. Once again, here's a function that I don't expect you to really know what it looks like. Even with all our pre-calc emphasis on transformations and basic functions and such, this one's a little bit too ugly to have a sense of what it looks like without a calculator. But once again, our first resort is to try direct substitution. So even though you get discouraged after a while because it seems to rarely work in calc, we should still try it. I plug 0 in here, 0 in here, and that gives me 1 over negative 2, or I could just call that negative 1/2. I can move the negative up, plus 1/2, all over 0, and darn it, there's our indeterminate form once again. Okay, so once again, we need another algebraic trick, and once again, we're going to use this theorem that says if I can change this function in just a very slight way that fixes the indeterminate form, that plugs the hole, then I can proceed and find the limit. So in this case, we've got a fraction within a fraction. We're going to be dealing with that a lot in AP Calc, so we better start getting used to it. And I'll preface this by saying that there are often many, numerous different ways one can do these. So I'm going to do it one way. If you try it a different way, and as long as you're using legitimate algebra and fraction techniques, there are certainly other ways one can go about this. First of all, I don't like writing fractions with that slash. I say always write your fractions with the horizontal dividing bar. Sometimes the book will do the slash to save a little bit of space, but rewrite it on your paper with the horizontal bar like this. Let's do 1 over x minus 2 plus, once again, horizontal bar, 1 over 2, all over x. And you may have noticed I left a little bit of space there because I was already thinking ahead as to what I want to do. I ask you, what do we usually do when we have a fraction plus or minus another fraction? In this case, a rational expression plus a fraction. What do we usually do? Well, we usually do common denominators, right? So let's do that. Let's think of what we need to multiply each of these terms by to get a common denominator. I see this 2 over here. It is not currently present over here in this denominator, so I'll put the 2 down there. And that means I need to put a 2 right here. Okay, now I've got a denominator of x minus 2 times 2. Over here, I've just got the 2, so I need to put the x minus 2. And if I put it on the bottom, I need to put it on the top. Learn to love these fractions. Not much I can do with the x on the bottom, so I'll just let it hang. All right, let's now that I've got a common denominator up here, let's go ahead and combine those two terms. I've got 2 plus 1 times x minus 2. I've got 2 plus 1 times x minus 2. All over that common denominator that I see here and duplicated here. So all over x minus 2 times 2. That's just the numerator, right? Now that's all over x. So I'm going to put that all over x and make sure we write the limit. And now I see a little stroke of luck here. I see that in that very topmost numerator, I see the 2 is canceled out by the minus 2. Okay, so let's go ahead and rewrite that. I'm going to take this fraction right here, and again, I'm going to say that that is x over, and again, I'm just going to leave things factored for the time being, x minus 2 times 2. That's my numerator, and it's all being divided by x, right? And here's where, pause and think about this. Isn't dividing by x the same as multiplying times its reciprocal, 1 over x? We're going to be doing that a lot. Dividing by x is the same as multiplying by 1 over x. That's what's going to get rid of this fraction within a fraction form. I still have not done direct substitution yet, so I still need to put the limit. There's the limit. But the clouds are starting to part, and I'm starting to see some sense of where this is going. I now see that I've got another great cancellation. I've got an x up here and an x down here, and they do divide each other out. And so now I've got the limit of 1 over 2 times x minus 2. I just reversed the order a little bit here. The limit as x approaches 0. And let's try our direct substitution. Now that I'm doing direct substitution, I don't have to write lim. I just write 1 over 2 times 0 minus 2. And that's going to give me 1 over negative 4. So let's say negative 1/4 is our limit. Put a box around it. All right, so let me show you. I didn't really show you earlier what the graph looked like. Well, here it is. And remember when we very first tried indeterminate form? If you watch the preceding examples, you should have come to expect that that means there's usually a hole in the graph, and you don't see it here. I should mention that. You're not always going to see it on your calculator. We know our calculators aren't perfect. Sometimes they don't show things perfectly. I will point out that if you were to turn the axes off, if you were to go to the format, which is right above your zoom button on a TI-83 or 84, if you were to go to format and turn your axes off, you would then see that the reason we didn't see the hole is because it was obscured by the y-axis. The hole was right here, but we didn't see it because the y-axis kind of appeared to fill it in. So this is where the hole is. That was where x equals 0. Come back to this image, and the limit we're interested in, x approaching 0, we realize that the y value of where that hole is negative 1/4. All right, I hope that made sense. You're starting to realize that a really solid grasp on algebra is going to be essential in AP Calc.